Okay, so let's resume then. So when we are writing scientific or engineering codes, it's often the case that we ask ourselves if our application, our code could run any faster, okay? So Samir S.Shende from the University of Oregon is going to show us some tools that we can use to take a look at our codes and see if there are opportunities for improving the performance. Samir, please.
Thank you very much, Asni and Tony. Thank you for inviting me here. It's always a pleasure to come here. I would like to thank my colleagues in the TAU Performance Tools project at the University of Oregon and ParaTools Inc. for their contributions to this project. So, the TAU performance system is a profiling and tracing toolkit. It's a performance evaluation tool that can highlight where your application is spending most of its time. It uses both profiling and tracing modes of measurement. If you look at performance evaluation tools in general, you'll find that most tools fall into one of these two categories. Profiling keeps track of the performance as the application executes. It has counters which increment every time a function entry takes place. So at the end of the program, the tool typically writes out a single record, a single line, which says MPI barrier was called 2,500 times and it took 30 seconds in all. That's a profiling tool. A tracing tool, on the other hand, can tell you when the entry took place and when the exit took place for every invocation of all the routines on all the threads. So it generates a lot more data, but the difference is you can tell what each process was doing at any given point in time. So there is a kind of a balance that you can strike between these two modes. And TAU supports both of these modes, and I'll show you examples. Now we can look at the cost of your code regions and attribute them based on wall clock time or even hardware performance counters. You know, these processors that we are running on, they have registers, and they can track low-level events that take place in hardware, such as data cache misses, such as cycles spent in a particular code region, the number of instructions executed, TLB misses, and so on. We use a package called PAPI to get access to that low-level information. But TAU can highlight the cost of your code using both wall clock time and the hardware performance counters. And its key strength is that you can automatically instrument your source code. And you can automatically insert the start and stop calls in a copy of your code. And this works at the level of routines as well as loops, I/O operations, memory operations. You can even define phases in your program and say, I want to see the performance based on distinct phases of execution. TAU runs on all HPC platforms, most of them, and it is free. It comes in a BSD style license. You can do whatever you want with it. It has support for instrumentation, measurement, and analysis tools. The one tool we'll be using in the hands-on, and I'll be demonstrating to you, is called ParaProf. ParaProf is TAU's 3D profile browser. So you'll hear a lot about different tools and over the course of the week, and you might get information overload. But the key thing to remember for TAU is that if you want to use TAU on most platforms, all you really need to do is change the name of your compiler to a TAU compiler script and set a couple of environment variables. Okay? It's as simple as that. You set the environment variables, put TAU in your path. You may load a module to do that, and then change a couple of environment variables to point to what kind of measurements you want to perform, and flip the name of the compiler. Build your code, run the executable, analyze the performance data. Is that simple? Everyone with me so far? Okay. So, as I mentioned, there are three distinct phases in TAU. One is the instrumentation or inserting the probes in your code. Okay. Now we've all done that at some point in our lives. If you want to measure the time spent in a loop, what do? We say T1 equals get time of day, T2 equals get time of day, and do a print statement and say time spent in the loop is T2 minus T1. That's a form of instrumentation. Okay. Similarly, with any of these tools, you have a start statement and a stop statement. And these probes that perform the measurement can be inserted in a variety of different ways. So, what I just described to you is a direct performance measurement. You are inserting the probes directly in your code. There is also indirect modes of performance evaluation where the system gives you an interrupt every so many milliseconds. Okay? And then you see the total number of interrupts in a given portion of time, and you can estimate how much time was spent in a given code region. So for example, if the program runs for 100 seconds and I get an interrupt every second and I get 100 interrupts, 30 of which are in a function called foo, I'll say reasonably the function foo spent about 30% of the total time of execution. Okay, that's the indirect mode of performance observation. TAU supports both direct as well as indirect methods. Okay, but I'll focus a lot more on the direct approach over here. I have some canned examples that we'll try on Carver. If you have any problems executing those, please let me know. I can see that most of you have your laptops. Are most of you able to log into Carver at this stage? Yeah? Haven't? We'll do that in the hands-on session after the break. We'll take a break around 2:15, right? 2:15 to 2:30, and we'll carry on over here. We're not going anywhere else. We're just staying here this time. Okay. So let me highlight again the key difference between profiling and tracing is profiling gives you the summary statistics. Okay, I want you to feel comfortable with these tools. I want you to feel comfortable with the output of these tools. So if you look at the performance data, you should be able to distinguish, is this a profile or is it a trace? Well, how do you distinguish that? If there is a timeline that shows you what happens when, then that's a trace. Okay? A trace comprises of a log of time-stamped events, and typically a file which has a table which says foo is 23, bar is 45, and so on, a kind of a table. This is used to recreate the actual execution of the program, and you can see when messages are sent from which process to which other process. Profiling, on the other hand, can only capture the total time and other statistics associated with a particular code region. So you can insert the instrumentation in your code using TAU in many different ways. This shows you some of the examples of how you can instrument the code. The simplest way that you may be most accustomed to is just manual instrumentation. Okay, if you're using Fortran, you just say call a TAU start and then call TAU stop and give it a name as an argument, and that's it. That's manual instrumentation for you, and you can instrument your code, link it with the TAU library, run it, and it can show you hardware performance counter data as well as wall clock time. The next one up is automatic source level instrumentation. You take the original code and using a preprocessor, create a copy and instrument the program. Also, the compiler can automatically instrument for you for most compilers. Okay, it can insert the calls to the TAU API, this measurement API, automatically. So you just get a compiler flag that you turn on, and then you get an object code which has the instrumentation. Now tau can also instrument at the level of the linker. You have many .o files, you put them together to create an executable. At that step, you can override some functions. You can say, you are going to use this malloc, don't use that malloc, use this malloc from tau. Okay, so we can redirect calls from one function to another, or the MPI library. We can create a whole wrapper library, wrap entire libraries, link them together, and create the executable. Tau can also rewrite an executable. It takes the binary, it creates another binary. That's an area of active research, and we are working on many different binary rewriters supported in tau, each of which has unique strengths for thread-based instrumentation or sequential instrumentation and so on. You can also instrument the program at the virtual machine level for Java. You can do hotspot compiler-based instrumentation. You can even do bytecode injection, selectively choosing which classes get instrumented and which others don't at runtime. And this works even when you have like bytecode that gets converted into native code and runs at full speed. We also do instrumentation at the Python interpreter level. How many people here are interested in Java and Python? A couple, okay. And most of you are interested in Fortran and C? Yeah? So we'll look at MPI, Fortran, C examples, but there is plenty of documentation on how to use tau with Java and Python as well, if you're interested in doing that. We can also instrument at the operating system level. So you have the user space program running, and if you wanted to look at what's going on within the OS, you can insert a loadable module from a package called KTau, the kernel version of tau, and you can also instrument in the kernel. It's not necessary, but if you wanted to see what else was going on, you can see that in KTau. So we have kind of exhausted the full range of possibilities for inserting instrumentation code. But the key thing is all of these layers pretty much target the same measurement API. And this API helps you decide what you want to measure. Do you want to measure the time spent in functions and write out a single flat profile, or do you want to capture the structure of the computation and show the full tree, the call graph of the program? Whether you want to profile or trace, use hardware performance counters or wall clock time. There are many different choices. And tau has some default options, but it has many switches. And you can tweak the instrumentation code by setting runtime parameters. And I'll show you a list of some of those parameters. So I again repeat that in most cases, all you really need to do is just change the name of the compiler, okay, set a couple of environment variables, compile the code, run it, and then you'll be able to launch the analysis tools. The analysis tools process the profile and the trace data. Now we have a trace visualizer called Jumpshot from the Argonne National Labs, but there are many third-party visualizers. The commercial tools like Vampire, and there's another free version of ParaProf that you can use with the tau trace data. In the profile side, we have support for a full profile analysis tool called ParaProf, which supports even a performance database. So instead of storing all the profile files scattered all over your file system, you can organize them neatly in a performance database. So you can delete those files, you can launch ParaProf, click to it, access the database, and then see the data. You can also connect a tool called Perf Explorer, which is a performance data mining and a cross-experiment analysis tool to do studies such as scalability studies. So you can, for example, track on the x-axis the number of CPUs, number of cores that each experiment ran on. Along the y-axis, you could plot the efficiency or the speed up that you saw in the code. And it can all operate seamlessly with the performance database. And if you want to share the performance data, instead of emailing large data files to your colleagues, we also have support for a TAU portal, a web page, where you can create multiple databases by just clicking. You can do it in a secure manner where you create your own username and password and invite others to view the data as well. So you don't need to, open up directories or email files around. You can do that all through the TAU portal. And you can even launch all of these tools that I described for performance analysis through the portal directly, even if you don't have them installed on your laptop. We can use Java Web Start to do that. So one of the tools that you will see a lot while instrumenting your program is a tool that we have developed called the Program Database Toolkit. Now, I mentioned to you that typically we just take the original source code and create a copy with all start and stop calls inserted nicely in the right places. Now that sounds too good to be true, especially when you look at the complexity of the languages that we target with Fortran, 95, Fortran 2003, C++ with templates. If you have ever seen like the vector or the map class, and you want to insert instrumentation automatically. Now, if I started a research project in my lab at the university, tried to just make a C++ parser, I can guarantee you that it will never really parse the real C++ source code. So what we did really is, we said, what is Intel using? What is Cray using? What is SGI using for their own compiler? We're all using Edison EDG parsers. Now they are like the gold standard for parsing C++. These guys are on the C++ languages committee. For C and C++, they make really good parsers. But they are a private enterprise, right? If you want to look at their source code, you got to pay like $200,000 or something. So we went and talked to them and said, we want to create a package where we can bundle all your stuff, parsing technology, and make it available for free, for commercial use as well as research use. So with the help of grants from the Department of Energy, we'd like to thank them for all their support for this PDT project, we were able to negotiate and get this technology. But the catch was we should be able to generate data from the parsing process, which can help us build interesting tools like the TAU Instrumenter. But we should not be able to compile the output. So it's not in direct competition with their other compiler users. And with that agreement, we could bundle these tools in binary form. And we ported it to a range of different platforms, every HPC platform you can think of. And we have these parsers for C, C++, and Fortran in a binary form that parses the source code, looks at the intermediate language, and emits the PDB file. This program database file has information like where does the program begin? Where do loops begin? What is the structure of the loops? Where are the I/O statements, memory allocation statements? Where are the call graphs? You can see the include tree, everything. Okay? It's got enough information for us to build interesting tools like the TAU Instrumenter and some other tools for static analysis. So that's the main static analysis system that we use in TAU. So what I would like you to remember is that wherever you see the word PDT appear in this talk, all it really stands for is this source analysis system where you can take the application source code, emit the PDB file, the parsed representation, and then use that in the TAU instrumenter to create a copy of the instrumented source code. Along the way, you can also give an instrumentation specification file that can tell you what to instrument and what not to instrument. You could say, I'm only interested in main and these 5 functions and nothing else. Don't instrument the rest of the program. Make the instrumentation really compact. When I run the program, it has a minimal overhead. I have reduced that overhead right down to 0.25%. So running it with or without TAU gives me very accurate results by just zooming into what is most interesting. I could even say for the first 3 routines, instrument at the outermost loop level as well. So I get just the things that are most interesting in my program and not 20,000 functions on each rank. So with this, I go to the next step of how do I really use this? I need to parse it. So what we did is we created compiler scripts. We called them tau_cc.sh for C, cxx.sh for C++, f90.sh for Fortran, even tau upc.sh for UPC. Are there people here who are interested in UPC? So we have support on Craze for UPC instrumentation. So what we do now is we need to use these scripts. Now if you log into any of these machines, you will find that typically you have 4 or 5 different compilers. You might find the PGI compiler, you might find the Intel compiler, you might find MPIG, OpenMPI. So it becomes difficult to identify which compiler, which MPI you're using. So what we do is when you configure TAU, you download and you configure TAU. This is, by the way, done for you, so you don't have to do it. You specify which compiler to use, which MPI to use, the location of different packages like PDT. And for each configuration, TAU creates a stub makefile. This makefile, if you just read it, has pretty much commands like, PDT is installed in user local, PDT 3.18, mpich is installed over here, use the PGI compiler version 11.1 installed in this location, and so on. But when it does that, it creates a stub makefile that looks like this. In the library directory, there is a makefile.tau-options. Now in this case, I have an option like MPI, PDT, PGI, and so on. So when you want to use TAU, all you really need to do is module load TAU and set the environment variable like this to the architecture lib directory, and then just change the name of the compiler. That's it. MPI F90 becomes tau F90.sh. Is that okay?
Mixed language. I have C, C++, and Fortran all together.
So what you would do in that case is you could just type make cc equals tau cc.sh, cxx equals tau cxx.sh, f90 equals tau f90.sh. It will override those 3 variables in makefiles and even the subdirectories where makefiles may be present, overriding the makefile variables, propagating the TAU scripts all through the project, and you'll be able to just compile your code. Yes? So what you're doing is you have a kernel written in Fortran. It's creating a .so file which is being imported in Python, right? So what you're doing in this case is you're first instrumenting the Fortran kernel. You have the .f90 file that's going to create a .o. So you are overriding the F90 environment, your makefile, with the tau F90. It will create an instrumented .o and an instrumented .so file. Python will load that file. When it runs, it will create the Fortran performance data. But you can do more. You can instrument at the Python interpreter level, and then you can import a package called imao and launch your Python program from there. So it will then instrument all the Python functions automatically, and those functions pull in the instrumentation from TAU. The thing you have to be careful is that you want to link in the TAU's shared A .so, so that Python and Fortran all use the same shared object to link with TAU. That's true of any package that you might use, whether it's a math library or TAU. You basically want to use shared objects whenever you have Python. So we have a TAU option called opt shared. When you set that flag, TAU option of opt shared, like this opt verbose, it pulls in the shared object for TAU. So with this, if you actually go to the TAU lib directory, this lib directory might be something like cray-cnl lib, or it might be x8664/lib, and just do an ls, you'll find various configurations of TAU. I mentioned to you earlier that there's a package called PAPI that we use for getting access to hardware performance counters. Okay. There's a package called PDT for source-to-source instrumentation, and then PGI as the name of the compiler. You could have Intel instead of PGI, for example. So what you see over here are these stub make files. One is for pthreads with PDT, another one is for MPI with PGI, one does PAPI with MPI with PDT and PGI. So you pick one of them, like this one, makefile.tau-mpi pdt pgi, compile your code, run it, and then you get ParaProf to view the results. Is that okay? So these are the only two steps that you need to do to compile your Fortran MPI program. Just choose an appropriate stub makefile. For example, you might have a program that uses MPI with pthreads, and you might say, I want to use hardware performance counters and automatically instrument my source code. So then you'll go looking for a file which says MPI with pthread, right? And if you look at this list, it's not there. So what do? You send an email to the Acts people and say, I would like this configuration. And they'll build it for you. And then you can set that as the TAU makefile and compile and run the program. This is the overview of ParaProf. It has many different types of displays, like histograms, like call trees, bar charts, and even a 3D display using Java OpenGL. So you can launch this to look at the performance data, and you can look at the database. And we have support for many different types of databases, including MySQL, Derby, the Apache H2, and Oracle and DB2. You can choose one. By default, TAU has like a H2 database that you can use to configure, store your performance data, and then show the results. We also support various different tools and read the performance data from different formats. So if you have data lying around from, say, gprof, you could load that in ParaProf and view it. This is the 3D visualizer. What you can see over here is the names of functions along one axis, the MPI ranks along the other axis, and then the height and the color can be set to the exclusive time or any other metric in your visualizer. Okay? You can rotate this in real time. You can move it around, zoom in, zoom out. You can even take these two sliders, like one is for function, one is for thread, and move those to a particular point in space and say, what's the value over here? Why do we do those sliders? Because it's really hard to click in a 3D space and reach a point that you really want to be at. So you just move between the thread IDs or ranks and the functions and reach a point and say, okay, what is the name of this function? It's right here. what is the height value, what is the color value. So you can see exactly how much time it has. But what this really gives you is a shape of the whole profile. You can see what each process was doing, no matter how many processors, all at once at a glance, and then zoom into a region, and you might be able to see things that are difficult to observe with just a stack of bar charts. Now this is a view of an application running on 2048 cores. But by just looking at it, you can see that there is MPI send. It increases in time from here to right. There's another function right behind that, the MPI barrier, and that's increasing in the opposite direction. So just looking at this 3D display, you can say, okay, MPI send and MPI barrier increase in opposite directions. And if I keep adding more processors over here, instead of 2,000, if I had 20,000, this might keep increasing like that, right? I might be wasting a lot of time in that. So you can see trends in the whole application, and then zoom in and say, why is MPI barrier and MPI send behaving in this manner? So I'm giving you real life examples. Like this is a code that we were running, and we and reduced the wall clock time from 500 to 70 hours. Okay. So such optimizations, we have many examples where we have gotten over 300% speed ups in your code by looking at what is the dominant code region, how do I focus on just that and experiment with a little kernel, try different communication substrates, try different algorithms to structure the data, and observe the performance before and after. Here is a communication matrix display. It shows me senders versus receivers. So there is a function here called find work. And this is an unbalanced tree search algorithm that's trying to find work in this function. I'm saying, show what is the extent of communication between rest neighbors. So I can see that when it looks at the nearest neighbor, it does a lot of communication, and then progressively it falls down. Okay. So I can generate such communication matrix displays by just setting an environment variable at runtime called tau com matrix equals 1. If I set that, I run the program which MPI rank. I can start the 3D communication display and then observe the extent of inter-process point-to-point communication. Pardon?
So go back to the previous slide.
The previous slide?
The diagonal is there. No, forward one.
Yes.
Okay, so the diagonal here is lit up, right?
No, it's the diagonal is 0. The one next to the diagonal is lit up.
So it's the next neighbor.
The nearest neighbor. So rank 64 with 63 and so on. So it's looking for work with its nearest neighbor. If you look at it over here, this is the thing that's lit up at the peak, and it says sender is 62 and the receiver is 61. It's not 62 with 62, that's just 0. So you can see. Yes.
That's a 2D version.
There is a 2D version too, yes. And in fact, it has the ability to scale to really large sizes. Like I've used that with like 16,000 by 16,000 cores in the 2D version. We also have a scatter plot in ParaProf. That is useful to look at one-off processors. If everyone is doing something in a regular manner and one of them is doing something else, you can identify the outliers. You can also look at, like in the previous slide, there's MPI send over here, MPI barrier over here, okay? And you can see this wall. It tells you when MPI barrier's time is low, MPI sends time is high on all these processors. So what I've done here is actually we have 3 different axes, and we have taken the 3 functions that have the most standard deviation. They vary a lot. And taken their minima to maxima, put them along each of those 3 axes, and chosen a 4th function and put it in the color axis. Now every rank has a unique value for all of these 4 functions. So we locate the x, y, and z coordinate and the color coordinate and put a dot over there for each rank. So every rank is shown in this with minima to maxima, and then you can see relationships between functions. Like here, I could see this wall appear for all those functions where all those ranks where there's a direct correlation. We also have a topology view. So do you remember this old machine called CM5 where there were all these different lights, and when the program was running you could see these different lights turn on, so you could see what each process was doing, right? So this is a topology display that reminds me of that machine. You have the 3D topology of the entire machine, and you pick one function, and you can see exactly what each process was doing on the entire system. You can pin it down, the processors exactly where they are located, and the topology view, the 3D view, and then this is from an IBM Blue Gene P system, but we also have this for Blue Gene Q, where we have a 6-dimensional torus. We take a 3D, and then we put this 3D torus cube on each vertex of another 3D cube. So we have a 6-dimensional structure, and then we can see exactly what each process was doing. We can even Z and see along in this plane what was the time spent in a particular function. So you can then see, for this case, MPI send has red at the top layer and blue at the bottom layer, and you can rotate it, you can see exactly what each rank was doing. Tracing is a very valuable tool, and we have, thanks to Argonne National Labs, we have support for Jumpshot in TAU. We bundle it and ship it as the default trace visualizer, and here you can now see all the processes along this y-axis and time along the x-axis. And you can see exactly what each process was doing, and click on it, and you can see, in this case, this is a SHMEM program, and you can see point-to-point one-sided communication calls, and you can zoom in and see what each process was doing. And if you click on an arrow, it will show you how it went from one to the other process. And to do that, if you have an executable built with TAU, all you need to do is export this environment variable called TAU trace equals 1, then merge the traces, convert them to a slog2 format that Jumpshot understands, and launch Jumpshot like this. Okay, so we've seen profiles as well as traces. How do you distinguish between the two? If you see the timeline display along this one dimension, you know it's a trace. It's showing you what happens when. In the previous function, you just saw the total time spent in MPI, send, and so on, right? So there are different types of events that we can use. One of them is the entry and exit event. It's most commonly used. You want to measure the time spent in a function, you have an interval event where you start a timer and you stop it. But there are also events that take place spontaneously program. You send a message. At the point of send, you may want to track the size of the message. Okay, you look at the memory used in your program, and the memory goes from 700 megs to 1.5 GB to 900 megs. It's varying the amount of heap memory used in your program. You want to capture that instantaneously. You want to identify the extent of variation of some system parameter that may or may not be monotonically increasing. Okay? To do that, we have atomic events. Atomic events can be triggered at the point of occurrence in the code at a given point, and then they can capture the extent of variation in the performance data. With the interval events, that is start and stop events, you can tell what is the exclusive duration in any function. So this is a very important concept. If there is a function called foo and it calls an instrumented function called bar, then you see this green region. This is the total inclusive time spent in foo, and if this is the time spent in bar, then you can subtract that from the total time to get this orange color, which is the exclusive time spent in this function foo. So you can say, I want to see sorted by the exclusive time all the functions. Which function spent the most exclusive time, and then zoom in on that. If bar is not instrumented, then its contribution goes into the parent. Okay? So it's only for instrumented functions. So instead of wall clock time, this color could be some count. It could be the total cycles spent in this function, or the total number of floating point instructions, or data cache misses. But what you have is exclusive and inclusive data cache misses, and you can then reason about them in the tool. So here is a simple display which shows you the interval events with the start and stop timers, and you can see the total time in MPI barrier over all 40 calls was 51 milliseconds. Okay, that is the interval event. It shows you the duration. There is a whole column here which says exclusive time spent in milliseconds and inclusive time across all the invocations. And then I also have an atomic event that shows you the extent of variation. It says here is the minimum value for the heap memory used at the entry, and here is the maximum value. There were so many samples that we collected, or the size of message for the broadcast from minima to maxima. So there are two distinct types of things that we are doing here. These are the atomic events, those are the interval events. Okay, we are looking at the extent of variation, and you see the name of that event. It says heap memory used at the entry of any function. Okay, now it would be nice if we could actually identify which function, right? The heap memory used went from here to there, and that is what we have with a concept called context events. Here I can now say the heap memory used at the entry of all functions, but at the entry of MPI barrier, the variation was from this 3097 kilobytes to 51 megabytes. That was the variation for MPI barrier. Whenever MPI barrier was called, and it was called how many? 40 times. That was the extent of variation of the heap memory used at the entry of this function. So now you have tagged a interval event and associated it with this atomic event. And you can do even more. You can even look at an edge instead of just a node. And you can say, when main called MPI barrier, this was the entry heap memory usage. So what I'm really doing is just look at the full call graph of your program and saying, these are the nodes and these are the edges. Along this edge, the heap memory used at the entry of this leaf node is so much. Okay, those are the context events, and you can get the depth of this by setting this tau call path depth parameter. You set it to like 100, it will go all the way up to main in your program. So there are several environment variables that I just introduced in the passing. I talked about communication matrix. I talked about tau trace, setting it to 1, generating trace files. Here's just a table that summarizes some of the environment variables that you could set. You can say tau sampling equals 1 to generate sample-based profiles. You could say tau track signals equals 1. What does tau track signals do? Well, if your application really crashes and it generates core dumps, and it generates core dumps from 2048 cores, that's a lot of core files to examine. So what you can do is compile it with tau and just run it with tau track signals equals 1. When it crashes, it will capture the call stack and store it with the performance data till that point of crash and create profile files. You can launch it in ParaProf and you can examine where each process was in the call stack when it crashed. Now we do that all the time with GDB, right? When your process crashes, you go and say GDB a.out core file, and then you say BT or backtrace and look at where it crashed. That gives you an idea about what each function or frame was in. This captures that in profile files. You can say tau call path equals 1 and turns on call path profiling. You can say tau track memory leaks equals 1. And then it will tell you where allocations were done, but deallocations did not occur. You have to run it with some tau exec tool to completely replace the malloc and free calls everywhere in the program with these counterparts, but you can do that. We also have support for throttling in tau, which is turned on by default. What does throttling do? When I instrument the program by just replacing one compiler with another, all the functions get instrumented. That means functions like min, max, swap, that might get called a billion times, will all access the system clock at the entry and exit. That's a huge overhead for something that trivial, right? So what tau does is, as the program is running, it checks. Whenever it sees a function that's speeding, that's going over 100,000 times, it says, wait a minute, what is the time per call for this function? If it is less than 10 microseconds per call, it says, no, this function should not be instrumented. It's going to excessively perturb the application. It's going to slow everything down. So it disables that function so that the next time it comes in, it just does an AND operation and just moves straight through that. It, of course, puts the name as throttled in that name so that you can identify which functions got throttled away. But then the program might start off slow but speed it up right away. And you can change those parameters. By default, throttling is enabled. You can disable it if you like. You can set the thresholds instead of 100,000 times and 10 microseconds per call. You might say, I don't care about functions that take 50 microseconds per call. That's still too low to want to measure some performance. You could tweak those parameters. We also have a parameter called tau compensate. It compensates for the runtime overhead of the tool. That means it runs a tight loop 1,000 times and says, what is the cost of a timer start and stop? Let me subtract this from the performance measurements and propagate that subtraction all the way to main through the call stack and clean the profiles before it's written out. How do we write a profile? Well, each process is independent. They don't talk to each other. They just write out a single file at the end. But we run at large scales. So you might be running on a machine like the Blue Gene Q at 160,000 cores or the Cray at 200,000 cores, you may not want each process to write out a single profile file, right? Because there's just too many files in the directory. You do an ls and you'll be stuck. You'll be stuck for like 15 minutes, right? There's a lot of exchange of metadata information for each file with the file system. So we have an option called TAU profile format where you can set it to merged. And what that does is everyone at MPI finalize globally reduces this data and writes out a single file. We even calculate statistics like mean, max, standard deviation, all at the end of the program, and only a TAU profile.xml single file is written out by rank 0. Okay? That's done in a very efficient way because we use MPI internally. So if MPI is using the the Torus network or the best possible network, that is typically the case for HPC machines, you will find that it does it in a very efficient and compact manner and create one single file. The last variable that I would like to talk about is this TAU metrics, where you can set different parameters of what you want to measure. You may want to say, I want to measure the CPU time, I want to measure the process virtual time, the wall clock time, the floating point instructions executed, the data cache misses. You can set them all in a colon separated list of TAU metrics, and then run the program. It will generate the performance data for each rank. Similarly, we also have compile time environment variables. You can set some of these options like compinst. What if you don't want to parse the program? What if there are errors? You can tell the compiler to instrument the code automatically by just saying opt compinst. Now you don't have to remember compiler specific flags, whether you are on an IBM system or a Cray system or a PGI compiler on a system like the IBM iDataplex, like Carver. You just set opt compinst and the compiler will take over. It will not let the PDT parser parse the source code. It emits a .o file with the instrumentation hooks in it. You can have opt track IO and wrap the POSIX IO calls. You can pre-process the Fortran source code. This is where you specify a selective instrumentation file. Recall, I said you can tell it what to instrument and what not to instrument. You can specify that in this manner. You can also create a wrapper library, external wrapper library, and point it with a wrap file option, and it will link that in. Here is an example of memory leaks in MPI using context events. I see total size, mean value, number of samples, max value, minimum value. I can see along which function there is a memory leak. Here, I see a memory leak right in MPI finalize. I didn't expect it. It's not application code, but it seems that it had like a memory alloc of 5 million bytes, and it just conveniently forgot to deallocate that when it came out. So, I mean, it was the end of the program anyway, and it just didn't deallocate it. So you can capture things like that. You can look at the IO statistics. You can see read and write calls and see exactly which files they accessed. Like here, there is a write which occurs on the dev infiniband uverbs0 file. You can see the total size of the write, whether it's a socket or a file. You can see the read and write bandwidth. What was the peak bandwidth, min, max values, and so on for the IO operations. So I have a couple of canned user scenarios. where I show you a figure from ParaProf that shows, for example, the exclusive time spent in all these routines. And if you want to generate this figure for, say, an MPI program, how do you do that? You just click and you go to the next page. These are the canned recipes. On Carver, just say module load tau. In fact, on all the NERSC machines, you can just say module load tau, and you'll be able to get this tau libdir set to the right value. Put tau makefile to one of these, such as in this configuration, there's MPI, PDT, PGI. Okay, this is good for an MPI Fortran application. Change my makefile so that I use tau f90.sh as the compiler. I compile the code, I run it, I create the profile file. Okay, is that about right? So let's make it a little more interesting. I can log into Carver and let me ask for 2 nodes and get onto the compute nodes over here. So I'm not doing any operations on the front end node. And now I am on the back end node here. I want to load tau. And now tau is in my path. I can say which ParaProf, and there it is, tau 221.3. Tau is there. I can say which tau f90.sh, which tau cc.sh. Okay? Now, let me start from a scratch. Okay? I create a directory called foo, and of course it exists. A new name, new dir. Okay, everyone has a foo directory. Here I say foo.c. I'll write a C program which uses MPI. I'll profile it. There is no file in this directory. I say include stdio.h. Okay, include mpi.h, int main, okay, mpi init, and then mpi finalize. Write out the rank, maybe even the size, right? MPI com rank with the MPI com world, and then the size similarly. Okay, and then I can print I am %d out of %d. I'm rank out of so many size. Maybe I should sleep some, okay, and say sleep for X seconds, and say my sleep for rank. So each rank is sleeping different amounts, and here. Okay, how do I compile this program? I write out cc as MPI cc. Say foo, so depends on foo.c, $cc, and clean it, bin rm-f, foo.o, foo, and any profile files. So I say make clean, make, and there I have it. Okay, first program, like the hello world. I can run it on, say, 6 CPUs, call it foo, and it's running. Okay. Now I want to profile this program. It's a simple C program. I understand its performance. I put in a sleep statement. Anytime you come across a different tool, don't trust it. Make sure that it shows you what you expect to see in a well-calibrated program and that you understand what it's doing. So if I want to compile it with TAU, the first thing I should do is I already have TAU loaded, right? I have TAU loaded over here. I say, show me the TAU libdir. And what are the files in the stub make files? Now this is a MPI program. I could just choose this one. It has MPI, PDT, PGI, same compilers that I'm looking for. So this is the step 1 in using TAU with any program. Set the TAU make file. Very important. You cannot skip that. Once you set the TAU make file, then look at your make file. What are you using for the C compiler? You're using a variable called cc, right? You want to override this with TAU cc. Make clean, clear it up. Instead of make, creating something like this, you can say make cc equals TAU underscore cc.sh. Okay? Drop-in replacement of the compiler name with TAU script. Now, what did I really do over here? If you look carefully, it called TAU cc.sh foo.c, which gives you foo. Internally, it calls the parser. The parser creates the PDB file that's fed to the instrumenter. Here's the PDB file. Here is the original source code, foo.c. It creates an instrumented C file. That instrumented C file is then compiled with your compiler like this, and it creates a .o file like this. We then link all those things together like this, pgcc foo.o, to create the executable, but also link in the TAU libraries and the MPI libraries. Then clean up the instrumented file, clean up the PDB file. If you want to peep inside and see what's there in that instrumented file, you can set a TAU option called opt keep files. Then it won't delete these files. You can look at what's there. But by default, it's like a regular compiler. So now I can run this on, say, 16 cores foo. Okay? So it will run one at a time. Each process is sleeping and then printing, right? So we see this clean output. And at the end of this execution, in my directory, if I do an ls, I'll see these profile files, one per process. And if I want to view them, I can launch ParaProf like that. This will load up the profile files, and I'll be able to then see how much time is being spent in all the functions. It shows me only one metric, one green dot says time, and this is the description of what machine it ran on, all the processor, command line options, how TAU was configured, and so on. And here is the profile. I can go and even click on 3D visualization. And here is the bar plot. I see that if I take this and move it here, this is MPI finalize. It's taking 15 seconds on rank 0. Okay? And if you scroll through it, it will show you the time it takes on each rank. If you go to the other one, that's my sleep. On rank 4, it took 4 seconds. That makes sense. It's sleeping for X seconds. And you can go up and see this simple profile. In the 3D view, you can zoom in, zoom out, right-click to translate. You can see exactly what the application was doing in the time. Yes, Osni? Okay. In 5 minutes, we'll take a break and then come back for hands-on. So everyone clear about what we just did here? We just instrumented the program and ran ParaProf. This is the tool we'll look at in the hands-on session some more. If you want to configure TAU, you can configure it with various packages in this manner. Like I'm saying here, use PAPI counters, and each configuration makes a unique stub make file. You can then set the TAU options. Here are some notes for Fortran parsing. If you're using a free format code in a .f file, you may want to pass the first one. If you're using compiler-based instrumentation, you can use that. Pre-process the source code. Here is how you can create an instrumentation, selective instrumentation file. I'll look at this for creating loop level data. And here is an example of a selective instrumentation file. I'm just saying instrument loops in all the routines. And then I pass that file as one of the TAU options. I'm saying, here's the selective instrumentation file that details what should be instrumented. Then I compile it, I run it, and generate the performance data. To use compiler-based instrumentation, I use this opt-comp-inst option. I can even compile it with loop-level instrumentation and measure flops. How do I do that? Well, floating point operations are counts that I can measure with this package called PAPI. It can measure a range of different types of processor events. And this package is a middleware from University of Tennessee at Knoxville. Here's the PAPI web page. And you can choose various hardware performance counters. Okay, you can see which events are available through PAPI. Here are some examples where I can see what comprises an event, what events I can choose together, and so on, and which events are available on this processor. There are utilities for choosing the events appropriately and choosing a particular configuration. To use PAPI, all I have done is chosen a TAU stub make file which has PAPI in its name. Okay, earlier there was no PAPI. Now this one has PAPI in its name. I set the TAU metrics environment variable which says use TAU metrics for time, floating point instructions, data cache misses for the level 2, and then compile and run the program. Once I get the profile files, now I see instead of just one green ball, I see floating point instructions, level 1 data cache misses. I can click on either of those to launch a ParaProf session. I can even compare various experiments in ParaProf. I'll show this more in the hands-on session, but look at this view. It's a list of all the functions sorted by the wall clock time. And it's showing me floating point operations per second. So I can see the top function is getting like 1.1 gigaflop, but the function number 4 is getting a mere 121 megaflops. So now I can zoom in and say, okay, this is the 4th most expensive function, and it's giving me only 121 megaflops. What's going on? How is the data cache miss ratio for this function? how does it compare with floating point operations, and so on. And I can look at this more carefully. This is a view of the call path profile, and I can see the structure of the program, like how main called the other functions in which order. And I can set that by choosing tau call path equals 1, and even a depth to which we can truncate the program call graph. And if you are interested in the trace files, you need to look at a common clock, and then it will show you a trace which shows processors along one direction and the time along the other direction, and you can see inter-process communication events in Jumpshot like that. To do that, all I do is set tau trace equals 1 and then run the program and create the merged profile file. After that, I can either convert to the Jumpshot format, or I can convert it to the Vampire format or any other third-party tool, and then launch the respective tool. We'll look at this with Jumpshot, and then we can see exactly what communication events took place. Now, I'll not cover this right now, but it's important for you to know that if you have an external library that you want to instrument and you don't have the source code for that, you can still instrument it by using a tool called TAU Gen Wrapper. It creates a wrapper library which can instrument the program in 3 different ways. This TAU Gen Wrapper just pretty much takes just 2 parameters. One is the header file, one is the actual library, and then it emits a library that it can automatically wrap like this. And here is an example of HDF5 where you can just wrap all the HDF functions and create a wrapped library which you link with your application, and you can see the performance. We also have support for I/O tracking and other things that you can do by preloading an application. So there's a lot more information here. We'll try to cover some of those things as we go through the hands-on exercises. Yes?
If you don't have the source code and it's not compiled with the symbols in it,
Still,
so how do you know which function is then taken?
it takes the header file and parses the header file, finds out the parameters, arguments, return values, and based on that, it creates another wrapper library that internally invokes between the tau timer start-stop calls the original library function. And you can preload such a library, you can even link it in at link time, and we have various examples like how to use this with different configurations with tau exec, this tool. And you can track memory, you can track I/O, event-based sampling, even GPU operations. You can wrap the calls to a GPU execution and then see what's going on. These are examples of scalability study charts from Perf Explorer and so on. Communication matrix, and
Do you have some of the GPU there?
I have GPU code execution here where you can see exactly which function called which kernel, what was the time for the upload and download, for which grids, block sizes, and so on. Even the variable equals A. Do you see this? Variable equals A at this file, this line number, and you can see exactly what the data transfer looks like in Jumpshot for CPU versus GPU. Just a show of hands, how many people here are interested in GPUs or looking at? So this might be useful. Talk to us and we can help you with a simple example first, and then you can look at this. Here's an example of a synthesized data set with like 1 million cores loading up in ParaProf, and we can see histogram displays. Now all the things I showed over here on the command line can also be done within Eclipse. within the integrated development environment where you don't need to remember all of these things. You can just see the source code, you can look at the database, you can launch the tools, all within a nice GUI environment. You can even select the hardware performance counters by just clicking on them and launching the jobs. We have also got support for running this locally on your desktop and connecting to the HPC system where the program execution takes place on the HPC machine, on the cluster, but the development can all happen locally, and you can see the results of the execution through Eclipse. For the labs, what we'll do is we'll just follow these 3 steps. Load the module, get this workshop tarball, and look at the README file and just follow along this file. I would like to thank our sponsors, the Department of Energy, Lawrence Berkeley Labs, and the ACTS Toolkit program, the Office of Science, Argonne National Labs, Oak Ridge, the NNSA ASC Tri-Labs, the DoD Mod Office, the National Science Foundation, and our partners at various universities like University of Tennessee, Oregon, Dresden, Research Center Jülich, ParaTools. And after the break, we'll take a 15-minute break, come back, and then do the hands-on exercises. Yes?